We are representing the University of Texas at Austin chapter, and we will be presenting about our district case for the University of Nebraska at Lincoln. There we go. So yes, our team consists of 9 members, and we have 5 present today to present. Myself, Forrest, we have Jeremy, Parthana, Ritvik, and Ali. Now our presentation has a couple different sections. So we'll start with our case background, a bit about our approach, some info about development and construction, our PV design, some battery storage info, and then finally a financial evaluation.
Starting off with some background for our use case, there are 2 main parts on the University of Nebraska Lincoln. The first part is East Campus, where we focused a lot on rooftop installations to offset the building load. The other part was City Campus, and we figured the university would want to use this campus, since it is in downtown Lincoln, to focus on more community-facing PV projects. One example we had is designing a solar flower installation in one of the fields on campus so that students can learn more about the photovoltaic installation that is going on. As for our approach, we have 2 main approaches. So the first is the approach to the PV installation. The second is the approach to the battery design. As for our PV installation, our main goal was to maximize the energy offsets for the buildings in total and to offer a competitive PPA rate to the university. As for our battery design approach, we wanted to design the batteries not to be for any economic gain, but rather to sort of serve as an emergency backup system to ensure the grid remains resilient during outages.
Now, in terms of the site plan, the University of Nebraska-Lincoln is located in Lincoln, Nebraska. The design of the system was completed in 90 days with iterative testing done to create a better design each time around. In terms of zoning, the University of Nebraska Building and Fire Safety Group serves as an authority having jurisdiction for fire, building codes, and safety codes. The University of Nebraska-Lincoln follows its own land use plan. In their master plan, they state that entities, including all local utilities, should strive to increase utilization of renewable energy sources such as solar. In terms of land use, there are no future land use of the area which we'll be using for our ground-mounted PV system. Using the information from the U.S. Wildlife and Fish and Wildlife Service, there are no critical habitats, minimal flooding risk, and no washes or topographical concerns. In terms of easements, in 2010, the Nebraska legislature passed legislation requiring cities and counties in Nebraska to assess, evaluate, and promote renewable energy sources and energy conservation measures as part of their comprehensive plan updates. This statement allows us to see that solar panels are not discouraged, but encouraged to be installed through local entities. Now, based on research of the process of installing a commercial size PV system, we identified the following timeline for our project. Now, the first part is assessment and pre-screening, which we approximated to take 10 days. This includes assessment of the site and environmental impact study and hiring consultants for other aspects of the project, such as civil, geotechnic, or structural. Next is the design and engineering. We approximate that to take 8 to 10 weeks. This includes a structural engineering analysis of the building to ensure it will support the weight of the solar cells. The solar cell design will be submitted to the utility. The electric design of the system will be completed and interconnect application will be submitted to the utility. Next, we have construction. We approximate this to take 6 months. The construction of the system also includes the procurement of equipment such as solar modules, racking, inverters, and transformers, as well as the construction of solar array and inspection and testing of the array. Finally, we have commissioning, which will take 2 to 4 weeks. This includes the electrical inspector signing off on the project and final inspections and the cleaning up the site being conducted. Now, along the journey of this construction plan, there are potential risks that might pop up. Some potential risks include policy landscape, weather, supply of equipment related issues, construction related issues, and underachievement. Now, during the pre-construction phase of the project, we plan to engage with the community and university by maintaining open lines of communication and holding meetings and drop-in events for them to voice their concerns. During the construction phase, we plan on starting construction later in the morning, not to disturb university residents, as well as updating the university with regular updates regarding road closures. Additionally, we plan to have the construction team use local amenities such as hotels and restaurants to benefit the local residents. After construction is finished, the system will be operated and maintained. The system will have to be operated and maintained, and this possesses another opportunity for community engagement.
As for the conceptual design of our solar system, we decided to start out with we followed a simple 3-step process to achieve this. So the first step was modeling the buildings using CAD software, and also modeling any obstructions that would shade the rooftop. The second step was to place the panels in accordance to the irradiance profile and applicable codes, which we will talk about in a later slide. And then the final step of the process, we strung the solar panels together, and we looked at the energy offset and how much they would save in utility costs. Across the board, we were able to create an average energy offset about 19% for each building, which we think would be really good in helping the university save money on their future utility bills.
For our conceptual systems approach, we plan on maximizing the building load offset, applying realistic constraints to installations, and maximizing PV capacity while also minimizing the interferences had on agriculture. Our system size is 4,032.9 kilowatts, and our annual energy generation was around 5 million kilowatt hours, which is the equivalent of powering about 500 American homes for a year. For our conceptual systems constraints, we constrained our system to the International Fire Code Section 1204.3, which demands for perimeters and interior pathway clearances, as well as setbacks for building roofs that have ridges. We constrained our solar access to 90% minimum, and for south-facing rooftops, we tilted them at a 40-degree angle. However, not all of our rooftops were constrained to this constraint to maximize the effect of our overall plan. The tilted rooftops, we added no tilt to avoid shading the northern facing sections of our buildings.
As for the system specifications, we decided upon using the SunPower E-Series commercial panels because they offer one of the highest efficiency rates in the market. They are 20% solar efficient, which means they're very good at converting sunlight into electricity. They're also high performance and rooftop compatible, which we think will help the installation process and overall performance. And we also decided to use the Fronius string inverters because they're high efficiency and the fact they're lightweight and durable. As for our ground mount system, we designed our ground mount system on the east side fields next to the Law College. We set a height of about 10 panels because we were putting this mostly over grass, which is pretty short. We decided to avoid any taller crops like wheat or corn because taller crops would need taller structures, which are more expensive. We also decided to put a spacing of about 14 feet to avoid any unnecessary shading to the grass. And we also avoided any research fields that were for the university in this area so that we wouldn't disrupt any ongoing research for the university. And overall, this grid allows us to sell energy to the utility since it's tied to a transformer, which allows the university to make extra money to pay back their energy offset and utility bills.
All right, and so on the distribution impact analysis side, there are two main parts we're going to go over. First up is the voltage impact that our design has on the grid, as well as the battery storage needs of the university and the sizing needed to meet those. So first up on the OpenDSS side, this was a software used to look at the voltage impact of our proposed system. And on the left, as we can see on the graph, the per unit voltage, it does decrease slightly as we increase our distance from the source. However, it maintains its tolerance in between that range of 1.05 and 0.95 volts per unit. On the right side here is just a graph of our grid configuration that we designed. So on the battery side, first thing we looked at was how long outages occurred within this district, and the average was 61 minutes. So we knew that having a high probability of meeting a 1 hour outage was necessary. Looking at this Python script that we made, the graphs are shown here. This is based on a relevant paper. We found that the 250 kilowatt hour battery size was the smallest size that was able to meet this 1 hour configuration or 1 hour outage survivability at very high confidence. On the graph on the right, you can see that it's near 100% confidence at 1 hour. However, 250 kilowatt hours was not the only thing we looked at. We also looked at the preserving the lifespan of this battery. So a couple of things we can control is state of charge. If we change the state of charge, we can change how long it's lasting. So we determined that the best route of prolonging our lifespan for these batteries, and in that way we save money by not replacing them, would be to keep the state of charge in between 85 and 75%. Again, that's a balance between allowing them to have a long lifespan, but also maintaining a state of charge necessary for that if an outage occurs, they could be used for emergency backup. So for that reason, we increased our amount from 250 to 325 kilowatt hours. Now looking at our total system size, 325 kilowatt hours of NMC lithium-ion batteries does have a high capital cost of $200,000. However, we believe it's worth it since it is supporting $2 million worth of inventory and has a very high probability of meeting that at a 1 hour interval.
Great. So now that we've looked at our design, we can dive into a bit of financial analysis, which will comprise of some system costs, our PPA rate, and a customer savings analysis. So first, we'll dive into the system costs. On the left here, you see a diagram of average commercial rooftop construction costs, and this varies with system size. And so for our 29 installations in the East Campus, we took a weighted average of these construction costs based off the size and settled on a value of $1.73 per watt for that construction cost. And as Parthana mentioned earlier, we already have determined our system size and our annual generation from the design side of things. So some other metrics that we needed to determine were the utility rate and also relevant tax incentives. So the utility rate that we found was most accurate and most common for this area was about 15 cents per kilowatt hour. And as far as tax incentives go, we did say that the federal investment tax credit at a rate of 26% would be on. Even though it is currently only extended at that rate through 2022, it has been re-upped many times in the past. And so we are relying on that continuing trend. And it's also worth noting that we depreciated our system with the maker's rate over the course of 20 years and used a customer discount rate of 8% for our net present value analysis. So with everything considered, our project sale price came out to be about $6.1 million. And while this is a hefty price tag, we determined that it was not needing any type of loan or debt to be taken out by the investor. This is because generally for the construction side of things, the developer is usually backed by a entity with deep pockets, and we deemed that it was not really necessary to take out a loan to finance it. So yes, so moving on from our cost, you can see that while there is that high initial capital cost, after about 9 years or so, the university will see its investment be break even. And after that, moving on towards the end of life, every year from there on will be profitable. And so with everything considered as well, we settled on a competitive PPA price of $7.9 per kilowatt hour AC. And we arrived at this by using a net present value analysis to even it out at $0 for a 20-year lifespan. And we feel that it's pretty competitive. You can see here that the PPA price does increase slightly every year, but does not increase as fast as the utility price, which is about twice the rate. And this can help explain the trend in annual customer savings, which is increasing every year, because as that margin between the utility and the PPA price increases, you're avoiding that cost and saving more money. So in conclusion, we feel that we offer a very competitive rate, and we really will help the university meet its renewable portfolios. And we look forward to any questions you may have.